This is currently my favorite math equation. My name is Matthew Petty, and I am a senior math major at the University of Arkansas. In honor of finally mounting my amazing whiteboard, I want to go over my favorite math equation, which is right here. This equation is known as Euler's identity, and it's described as e to the I pi plus 1 equals 0. And this should raise some red flags for anybody who's had a little bit of math experience, because e, a positive number that we know, raised to any power should never be negative. But we have a positive number plus 1, which is positive, equals 0. So how does that make sense? Well, I just took a class this past semester called Complex Variables, where it's essentially calculus just with the imaginary numbers. And I learned why this equation actually works. So let's quickly go over what an imaginary number is. An imaginary number is denoted by I, and it is the square root of -1. With I, we can create what are called complex numbers. I'm going to use the variable z, and complex numbers have a real part and an imaginary part. 1 plus I. So the real part is 1, and the imaginary part is I. And you might be wondering, how can I graph this? Well, on the complex plane, the x-axis are the real numbers, and we denote that by RE. And then the y-axis, we denote IM as an imaginary. So to plot the complex number z, we would go over 1 and then up by I. I is here, and so we get this dot right there. So that's where our complex number will sit on the complex plane. You can think of I as like increments of 1. You're technically not supposed to say that, but visually that's what it looks like. So now this begs the question, how does any of this help us understand Euler's identity? Well, we're going to have to use something called polar coordinates, which basically takes a number and makes it into like a circle. Okay, so the basic form of polar coordinates are as follows. So we take our complex number, and what we can do is we can describe it by r e to the I theta. And basically what this does is it turns our complex number into something that we can use, such as the unit circle. So we have a radius right here, and then we also have an angle right here, our angle being theta. So our goal is to take e to the I theta, or e to the I pi, I'm sorry, e to the I pi, and make it equal to -1. So since we're using polar coordinates, let's bring the unit circle so that we can use it. Okay, if you know your unit circle, it has a radius of, you should know this, 1. So right here. And we can use different angles to get different values on the unit circle. So I'm going to call this unit circle. Okay, y'all doing good? Okay, so on the unit circle, depending on which angle you're using, will give you a value. So if we are using theta equals 0, well, we start right here, and we're not going up or down at all. So we just stay at 1. So technically, e to the I 0 would be just 1, which makes sense because e to the 0 power should be 1. Okay, but now what if we do the angle pi? So if you remember your unit circle, pi will take us all the way over here. And what's this value right here? It's -1, which is kind of crazy because that's exactly what we need. So all we're doing right here with Euler's identity is taking a complex number, converting it into polar coordinates right here, and then finding which angle gets us to -1. And that is why Euler's identity makes sense. Thank you so much for listening to me yap. I'm a math major, so you're probably going to see some more math content. But anyways, I'll see you guys later.